everybody. This is Austin Hoggett here to give you another lecture from OpenStack's Elementary Algebra. Today we're going to be covering section 2.4 and understanding the general strategies used to solve some linear equations. This is a critical skill set that you'll need to move forward into the section coming next on graphing. So understanding this content is imperative, and practicing, getting your hands dirty with some of these questions is really the best way to understand how to utilize sort of the strategies presented here. All the properties of equality that we mentioned in previous sections now come into play. So we'll see some variety of how questions might be presented to you and how to handle those situations. But I can't give you a prescription for how to solve every single problem. So the purpose of mathematics, of course, is not to follow a recipe. We're not baking anything here. It is a problem-solving mechanism. And so we have to think creatively with the tools that we have. So talk a little bit about this general strategy with some examples, but we'll also talk about how to classify three different types of equations. There are actually more than one particular type of equation that we'll come across in this course, and how those questions get solved differs quite a bit. So we'll take a look at those as well. So the first thing we'll discuss is sort of a rundown of this general strategy described within the context of these linear equations. So they give me a step-by-step here, and as per usual, they start with simplifying as much as possible the question as it's given to us. Now, what we talk about when we mean simplify, we mean things like take and distribute your terms. If I have, for instance, something that involves distribution, as you might see here, then we would want to go ahead and multiply that across. In other words, reduce the complexity of the problem as much as possible before we do any of the algebra steps necessary. This also might include combining like terms. So for instance, if there are redundant constant terms on the left or right hand side of the equation, we might combine those together first, again, prior to implementing any algebra steps. All right, so the next step after that, once we've simplified the question as it's presented to us as much as possible, typically we want to collect our variable terms on one side of the equation and our constant terms on the other. Which side of the equation is sort of irrelevant. Typically, though, you'll find that moving your variable to the left side is pretty common, simply for the fact that at the end of the question, we get, if our variable is x, let's say, x equals some number at the end, right? So I would kind of lump step 2 and 3 here together. The idea that we want to move terms from one side or the other typically involves this addition or subtraction property of equality, and that's true whether we're talking about a variable or a constant. So once we move terms by this use of the addition or subtraction property, usually we will then have our variables on one side, constants on the other, and we're asked to consider how do we get our variable to have a coefficient of 1. Right? So the ultimate goal here is to isolate the variable. You'll hear that phrase used a lot in describing this process of algebra. When we talk about isolating the variable completely, not only do we want to remove all the other terms, but we also want to make the coefficient equal to 1. And the way that we can do that is through the multiplication or division property. So that typically is the next step of algebra. So again, the addition subtraction property, most of the time, not always, will come first, followed then, once we've separated those constants and variables from one another, with the multiplication or division property. So at the end of that process, as I said, we'll get, regardless of what our variable is, let's say x equals to some number. At the end, we can then check that we actually got a solution that makes sense. This becomes critical as the level of complexity of these problems increases. So when we talk about checking the solution, if there's like one step to the solution, maybe it won't be such a big deal to avoid this particular part. But we're building sort of behavioral strategies by talking about this generally. So getting in the habit of checking that you have a correct solution will help you as things get more difficult along the way. So checking the solution involves, again, replacing what we think the answer to our variable is back into the original equation and making sure that we get, again, what we refer to as a true statement. Something like 5 is equal to 5 or -7 is equal to -7. Those are true statements. Right? So we can always verify that the computations we made along the way in those first few steps were accurate by checking through this substitution process. So let's demonstrate these processes with several examples here. So the first one I pointed out involves a little bit of distribution. Um, if you don't recall, distribution typically comes in the form, and I'm using kind of generic expressions here, some expression outside of the parentheses multiplied by both of the terms inside of parenthetical. So a specific example of this illustrated here, we show that we have something like, and I can read this as -1 times y plus 9. Right? Now, some students refer to this coefficient outside of the parentheses as -1 so that they can more easily digest the process of distribution that's shown here in the top left corner. So that's our generalized expression for distribution. If I apply that in this case, I can reduce this expression to something like -1y, and -1 times 9 is just -9, right? So on the right-hand side, there's not really anything that we need to simplify or do distributions for. There's no combination of like terms to worry about. But here at the first step, we can do this distribution. All right, so from here, we now have, again, our variable term, -1y, and typically we won't really write the -1 here, so I'll write this just as -y. -1y minus 9. We want to get that variable by itself. So what was the next step? Typically, we said that we would use the addition or subtraction property to move constants and variables from one side to the other. So in this case, I have uh, I'm subtracting 9 from that variable, but I'd like to undo that operation essentially. So we will introduce the operation of addition by 9 to each side. That does two things for us. It would maintain the initial equality, right? If each side is equivalent to one another, then these properties of equality can be implemented without changing the assumption that that's true, right? So -9 plus 9 is 0, and we're just left with the variable by itself, -1y. 9 plus 8 should give us 17 here. So we're left with, again, this variable and constant separated from one another. But the trouble is, our variable is not quite completely isolated. We could still say that, as I mentioned a second ago, the coefficient here is really -1. Well, we want it to be +1. We need y by itself. So we could either use the multiplication or the division property to undo the operation being presented here. Now, normally if my coefficient is a whole number value, we'll use the division property. So I could argue that division by -1 here is appropriate. At the same time, though, if I use not the division property, but the multiplication property, I could use the multiplication by the reciprocal in cases where I have a fraction. But it turns out in this instance as well, if I multiply by -1 on each side, I'll also end up removing that coefficient. Right? So -1 times -1 gives me +1y. -1 times 17 is -17. So regardless if I use the division or multiplication process here, I will end up with my variable isolated, getting a numeric value on the right-hand side for the solution here, y equals -17. So again, one of the steps that we show here, and this is per usual, is the addition or subtraction property. We could also use the multiplication or division property. So that is usually the sequence of events in these cases where we're asked to solve a linear equation that has, again, maybe 2 or 3 steps of algebra. All right, so the last thing that was mentioned is that we should be able to go back and then check the solution that we think we have is actually correct. So how do we check in this case? Well, we'll take what we think our solution is, y equals -17, and plug it back into the original equation here. So if I make a replacement here for y of -17 plus 9, all of that should be equal to 8, like this. So if I follow PEMDAS, the order of operations here, we could say, well, that something like 9 minus 17, or said the other way around, -17 plus 9 Either way, we get the same thing here. We should get negative 8. All right, so what is the opposite of negative 8? Well, the opposite of negative 8 would be positive 8. So I do get a true statement here, which shows that, yes, this does in fact confirm y equals negative 17 was correct. That is our solution. So that, again, demonstrates sort of the basics of this process. At the outset, I'll either have to do some type of distribution or combine like terms, followed then by moving constants and variables from one side to another. For this second step, I use the addition property, but it could be that we have to use one or both of those addition subtraction properties to do the manipulation. Finally, once we've separated, as I said, the variables to one side and constants to the other, we'll use the multiplication or division property, and we've described instances in which you would choose one or the other for that. So let's look at some more examples here and kind of show how the complexity can be increased. So here is an example that clearly I have a distribution of sorts that could be done from the outset. So as I see this expression here, I have 5a minus 3 plus 5 is equal to negative 10. Well, here is my distribution pattern. Again, so I'm writing out the arrows to indicate what needs to be multiplied together. So 5 times a, and then negative 3 times 5, that should give me minus 15. We also have this constant on the left-hand side, plus 5 still, and minus 10, like this. So again, we're describing here, as I've shown it with the arrows, a type of distribution that then we can use to simplify further by combining like terms. So what are all my like terms? Well, on the left side, I now have two constants that I can combine. This reduces then our expression here on the left to 5a minus 10 equals to negative 10. All right, so now is the point at which we can use our algebra steps. We've removed all the redundant terms from each side of the equation. So what is the algebra step that I'll implement here? Well, we use the addition property of equality. Getting lots of spikes in my writing here, sorry about that. So how do I do the addition property? Well, in this case, I want to isolate 5a. I'm going to ignore the coefficient for now and just try to get rid of all the terms other than 5a. So instead of minus 10, I'll do the opposite, add 10 to each side. There's the spikes again. All right, so when I simplify here, we get that these additive inverses, 10 minus 10 is 0. So I'm left now with just the term, my variable, 5a. And we actually get another cancellation here, so 10 minus 10 is 0. So it looks like the last step that we'll need to do is the division property. So bonus points if you can tell me how this would be done with the multiplication property. In this case, since my coefficient is a whole number, we can just divide each side by 5, right? Well, what would be the same way to do this, not as division but multiplication? We can multiply by the reciprocal of our coefficient. If my coefficient is 5, that means the reciprocal would be 1 over 5. So again, division by 5 and multiplication by 1 over 5 gives me the same computation here. I'm left finally with the solution. We get a is equal to, well, 0. 0 divided by 5 is still going to be 0. And so there we have our solution. And of course, the last thing we want to do, at least to show that this can be done consistently, is to check that what we think is the answer is really going to give me a true statement back into the original equation. So by substitution here, we get 5 times 0. Suspectedly, we think a is equal to 0 is our solution. So 0 minus 3 plus 5 is equal to negative 10. And again, we follow the order of operations now to simplify as we go along. So 0 minus 3, that's just going to be negative 3. And simplifying that further, we get negative 15. And finally, we can show that indeed we do get a true statement. In this case, negative 10 is equal to negative 10. So since this is true, that verifies that yes, a equals 0 is our solution for this example. So as I said, not every problem will follow this exact series in terms of how we go about solving it, but this is at least a good general strategy to start with, right? So here's another example. And what I'll point out about this case is what makes it different is the fact that my variable actually shows up on both sides of the equation. In the previous examples, we showed how, again, we can start a problem like this through the process of distribution and trying to simplify uh, the equation prior to implementing any algebra, but we'll actually find, unlike the other examples, that I need to move constants to one side or the other as well as variables. So there'll be an additional uh, step of the, well, addition and subtraction properties. So let's look at the distribution to begin with. Just like last time, I can take and multiply across each of the terms here. I get 2/3 times 6m plus 2/3 times -3 is equal to 8 minus m. Simplifying these computations, I might say, well, 6 divided by 3 is 2, and 2 times 2 is 4, so that should give me an expression here, 4m. Now, I'm using this division part here, so -3 divided by -3 divided by 3 gives me -1. -1 times 2 just gives me -2, like this. So notice I'm taking the residual of that division and multiplying it with a numerator for each of those two terms to get my computation. All right, so my right-hand side, again, still looks the same. I get 8 minus m. And again, I pointed out this at the beginning. We have now a variable and constant on the left side, as well as a variable and constant on the right. Even in its simplest form, I still need to use the addition and subtraction properties for terms to shuffle this around appropriately. So as I said, typically I'll move my variables to the left-hand side of the equation and constants to the right. How do we move terms, though? So let's take a look at just the left side of the equation. 4m minus 2. If I want to undo the operation of subtraction here, we do the opposite, which is addition. This is how we move the term. So if I add 2 to one side to maintain the initial assumption that these two sides of the equation are in fact equal, I got to add 2 to the other. So as I simplify here, we remove the constant term from one side of the equation, and on the other, we end up here with 10 minus m. So how can I get the variables to be on the same side? Well, we'll do the same sort of process here. If I want to move that term, I need to undo the operation of subtracting m, which is, in this case, adding m. So by adding 1m to each side of the equation, these are additive inverses of one another, meaning they'll cancel out, leaving me with 10. And on the left-hand side of the equation, this is 4m plus 1m equals to 5m. So we actually had, as I said, two addition properties to be implemented for a problem where we have to move constants and variables. So the last step here, now that we've separated those variables and constants, is to use the division property. So we divide each side by our coefficient here to get m is equal to +2 for our suspected solution. So just as before, just to be clear, we want to check that what we think is correct really is true. I could have botched, some of the computations along the way here, or certainly here during my distribution process. So it's always helpful to go back and check if we have possibly made a mistake in our computations as well as the algebra. All right, so by substitution, we were replacing 6m with 6 times 2, like this. On the right-hand side, we get 8 minus 2. All right, so simplifying. I can do this a couple different ways, but let's start with the right-hand side of the equation. 8 minus 2, that should give me 6, like this. On the left-hand side of the equation, before I do a distribution of sorts, let me sort of scale this down a bit, 2/3. Let's look at the computation here. We get 6 times 2 is 12. Okay, so what is 6 times 2? That's 12, and 12 minus 3. Okay, when we do that computation, we should get something like 9. So we have now a fairly easy multiplication problem. We could do this in a couple different ways. We could say 9 divided by 3 is 3, and 3 times 2 is 6, such that we get the true statement here, 6 is equal to 6, verifying that we have a correct answer here. We could have also done this computation as 9 times 2 is 18. 18 divided by 3 is 6. Right? So either way we do it, um, our confirmation holds up that m equals 2 is the solution in this example. So as I said, that general strategy describes the usual flow of events for these algebra steps. Being able to pinpoint which property is being used is less critical, in my opinion, than to know which step is next. So we need to be cautious about checking as well, making sure that the computations we make along the way are solid. So one last example of this, and we'll move on to different types of uh, equations, the classification aspects. So the last example we'll show here illustrates one of the more complicated versions of this that we've seen so far, where the initial problem given to me does require a great deal of distribution and simplifying before we ever start the algebra process. So take a look at this example. We're asked in the left-hand side of this equation to do certainly lots of distribution. So I've got 4 times x, 4 times -1 here. That will reduce to give me 4x minus 4. We also have the constant minus 2. On the right-hand side, we have, again, another distribution. So 5 times 2x should give me 10x. 5 times 3 should give me plus 15. And again, we drop down our other constant. So certainly there's a distribution, but now we have constant terms like terms on each side of the equation that can be reduced. And I'm left here now with something like 4x minus 6 equals 10x plus 21. So we did our distribution, we did our combination of like terms. We ended up again with a case where we have variable and constant equals variable and constant. So shuffling around as we did before, I can choose to move terms around differently than we showed a minute ago. In fact, let's do that just to illustrate the point that it doesn't matter which side I move my variables to. It's just a matter of habit that I typically move variables to the left, constants to the right. But let's show how that can be done in the opposite for this example. So in this case, if I want to move my variables to the right-hand side of the equation, I'm going to, instead of working on 10x, I'm going to work on 4x here. So we want to do the opposite, which is to subtract. So minus 4x on each side leaves me with 0x minus 6. And on the right-hand side, we get 10 minus 4 is 6x plus 21. All right, so now we need to move that constant 21 to the right-hand side. We do that by subtraction here. So by subtracting each side here, I end up with the expression 6x is equal to -27. All right, so now what we have is the expression -27 is equal to 6x. That coefficient needs to be simplified by dividing each side by 6, such that we get x is equal to -27 over 6. Now, if you absolutely hate that this is in an improper fraction form, you're welcome to write it another way. We might write this as, let's see, the mixed number format would be -4. Let's see, that would give me 24 with 3 left over, so 3 out of 6, or -4.5, or -4.5 if you prefer the decimal version of this. So there's a couple different ways that we could write our solution out, and sort of all of these would be equivalent. So it just is a matter of what is presented as your manner of reporting the answer. Do you have multiple choices that you have to select from, or are you just demonstrating the work? So there's how we get to our solution, and just as before, we might want to check that this is correct. Now, I'm kind of out of space in this instance. Certainly there are ways to check this by calculation in the calculator. That's a lot easier than to show it all by hand. In other words, just replace x with -4.5 on each side and figure out, do I get the same thing on each side, right? And write that out. So we can go through that process more quickly with the calculator in retrospect once we have something to actually check against. All right, so as per usual, we'll now move into a slightly more complicated zone of this topic. We want to look at now what we call the different classifications of these types of linear equations. And there's only three. Now, the one that we're most familiar with is what we will start with. The conditional equation is the one that we are most familiar with and the one that we'll come across the most often. What we mean by a conditional equation is one that is true for one value of the variable and false for all of the others. So here's a simple example of a conditional equation. We might find that our equation is something like x plus 1 equals to 2. And I might pose the question, what are the values of x that makes this equation true? Well, we can use our algebra to actually solve this thing and say, well, if I subtract 1 from each side, we get that these cancel and 2 minus 1 is 1. So x equals 1 is my only solution. And sure enough, we can go back and check that. Does 1 plus 1 equal to 2? And the answer is yes. So x equals 1 is the only solution to the equation. All right, so when we plug in any other value of x, of course, we'd get a false statement as opposed to the true one that's shown here. So how we come across most of our equations is that we go through the algebra steps. We can either verify that the solution we got really does give me a true statement at the end, but regardless, we should get x equals something at the end if this is a conditional equation. In other words, the equation is only true on the condition that x equals that particular value. Okay. Now, the next two that you see here, that was, again, the first type of equation. The next two that you see are the identity and the contradiction. Now, these actually are opposites of one another, but they have something in particular that is in common. If I have an identity or a contradiction equation, unlike the algebra steps that we showed here that led us to a solution, when we try to solve either the identity or the contradiction equation, not only do we not get a solution, our variable typically disappears entirely. So for the identity, it's an equation that's going to be true no matter what value of x or y or whatever the variable happens to be. No matter what value I choose, I'll still get a correct number or a true statement. So why might this be? So let me give you an example of an identity equation. So simple enough, I could say that something like x plus 1 equals x plus 1 is an identity equation. Why would this be the case? Well, I want you to close your eyes for a second and pick a number and ask yourself, what happens to that number if I were to replace it into this equation? Well, on both sides of the equation, I would take whatever number you just picked and add 1 to it. So inherently, that value that you randomly chose would pop out on the other side of the equation, right? So there's this equivalency no matter what I do, no matter what variable or what value you choose, that the two sides will always be equivalent to one another. And the identity part of this comes from the notion that I can basically see a mirror image of the expression used on both sides of the equation. Now, it may not always be so obvious that I have an identity equation. So, for instance, another example you might have is something where I have a distribution of sorts. So let's say I have 2 times 3x plus 1 is equal to 6x plus 2. This is another identity equation, although it's maybe not obvious from the outset. So in each of those cases, what we mentioned is that something odd happens when I actually try to use algebra to solve them. And perhaps let's use the first example here to illustrate what happens. If I wanted to move the variables to the same side so that I can isolate that term, what I would find is that I end up deleting them entirely from the problem. Okay, so in this case, x minus x is 0, plus 1 is 1. Again, x minus x is 0, plus 1 is 1. All I'm left with is a numeric expression, 1 is equal to itself. Okay, well, that's fine and happens to be true, but what does that tell me about the solution? Well, the solution is that any number I pick would give me a true statement in the original equation. So how do I convey that type of answer? Normally we have x equals something. How do I convey x equals whatever you want, buddy? So we can represent solutions in a couple different ways. Certainly, x equals a number is the common version of this. There's some other ways that we could represent it. Um, in this case, we could use a capital R with a sort of extra line drawn through it that represents this notion that all real numbers would make a solution in this case. We may also show that the interval between negative infinity and positive infinity represents all real numbers. That would give me a solution to this equation. So the identity, as I said, will be instances where the expressions on both sides of the equations, obviously or not, end up being the same. And as we try to solve those identity equations, we will end up removing the variable and be left with a true statement. So that we can then confirm, yes, well, any value I would have chosen would have made this true, so it doesn't matter. The third sort of type of equation that we might have is the contradiction, which is just the opposite of the identity. If all real numbers are a solution in the identity equation, there is no solution in the contradiction equation. In other words, our variable, just like in the identity, disappears while we're trying to solve it, only now we're left with a false statement. So again, how do I convey that there is no solution to an equation? Well, there's a nice succinct way to write this as well. We could use something that looks like a circle with a slash through it. This says that the solution set is empty, right? So the solution set, the set of values that makes the statement true, is empty, right? So again, I'll give you an example of a contradiction equation. Let's see, if I have something like x is equal to x plus 1. Although that looks trivial to solve, this actually does not have a solution. There's no value of x that will make the two sides equivalent to one another. And hopefully this makes some sense if you take a moment to consider, again, randomly picking a value of x. What's going to happen here is that one side is always going to one-up whatever value you picked, right? So let's imagine I choose 5. Well, what happens is, well, I put 5 on the left side, but I get 5 plus 1 on the right side. So I'll get 5 is equal to 6. Okay, well, that's not true, okay? So that particular value is not it. But I can't just keep, guessing and checking. I want to use the algebra again to demonstrate how this can be solved. Again, when I try to move my variables to the same side, they disappear. Only this time I'm left with something like 0 is equal to 1, which is, again, false. This is a false statement. That's telling me then your variable's gone, the statement left is false, therefore there is no solution. There's no way for the two sides of the original equation to ever actually be equivalent to one another. So what we mentioned in a previous section here is that all these properties of equality that we use for the algebra rely on the assumption that if A is equal to B, then the properties of equality will maintain that assumption. But it is just that, an assumption that is not always correct. So these contradiction equations prove the point that we can do all the algebra steps correctly and still not end up with a solution. So the identity and contradiction, as I said, share the similarity that when we go to solve them algebraically, the variable disappears. But if I'm left with a true statement, I'll have had an identity equation to begin with. If I'm left with a false statement, it must have been a contradiction. So let's go through a couple of examples here to practice classification of these types. So here's the first equation that I'm given. It looks to me that there's lots of distributions and simplifying that needs to be done first before we ever get into the classification part of this. So to begin with, let's do that. So showing my distribution here with the arrows, I get something like 6 times 2n is 12n. 6 times negative 1 should give me minus 6. Then we bring down our other constant here, just plus 3. On the right-hand side of the equation, I've got 2n minus 8, and then we hit our distribution, which looks something like this. So we get 5 times 2n, that's going to give me plus 10n. 5 times positive 1 should give me just plus 5. So for our like terms here, you can see that we have constants and variables on the right-hand side that are like terms. We end up on the left here with 12n minus 3. Looking at my variables on the right-hand side, we get 2n plus 10n is another 12n. Negative 8 plus 5 is negative 3. So I can actually tell you and identify from the fact that the equation has expressions that are exactly the same on each side, that this must be an identity equation. It must be an identity equation. No matter what value of n that you would replace in this equation, the two sides would be equivalent. Now, it was not obvious from the initial outset, but of course, at this stage of simplification, we've done no algebra to show that this is true, but we can see that is where we're heading. So again, if I try to solve the thing, my variable just sort of disappears. However, in this case, I'm left with a true statement. Negative 3 is equal to negative 3. Since this is true, it must be that we have all real numbers as the solution. Again, we could state that in a couple different ways. We could say that either all real numbers or from negative infinity to positive infinity. Now, one thing I'll sort of add on here is that if I'm going to use the interval notation, it's likely going to be buried into a set builder type bracket system. So we have a curly Q bracket, we'll declare a variable, we'll say where, right, with this vertical bar, x is anywhere from negative infinity to positive infinity. So the set builder notation will look maybe something like this, where we declare the variable, our vertical line here says x where, and then we give whatever solution we have. Okay, so that would be maybe one additional thing you might come across, in particular in WebAssign. So that tells me then again that this is correctly identified as the identity equation. So let's try another one of these. All right, so again, from the outset, I have no real idea as to what type of equation this is. So as we go through all of these, notice that we're just having to solve in each case. We can think through some parts of the question to kind of expedite an answer, but not always. So by distribution, I get something like 4 times p and 4 times negative 5 on the left side of the equation, set equal to 0 like this. I've got these constants now that we can combine. So 10 minus 20 should give me negative 10. So rearranging a bit, we get 4p minus 10 is equal to 0. All right, so I don't see any of the sort of oddness of the previous examples. What it looks to be in this case is that we'll end up with an actual solution at the end. So we get these canceling. I'm left with 4p is equal to 10. And then by division of 4 on each side, we end up with an answer here of p is equal to 10 over 4. Reducing that, we could say that they are both going to have a common factor of 2, reducing this to 5 over 2. Or if you prefer, we could say that's 2.5 or 2.5, like this. So we get something at the end for our solution. That tells me this must be a conditional equation. The equation or the equation itself will only be true if p is equal to this value or any of the equivalents that are shown here. So that must be the conditional equation. All right, so as you might have guessed, there's one last example to show here, and we've only got 3 types of equations. So this is an example of the contradiction, but as I've mentioned all along, that's not at all obvious. I'm just looking at it from the beginning here. So let's show how this last example illustrates a contradictory equation. So just as before, we'll start down the process with the assumption that, yeah, the two sides are really equivalent, so I should be able to find the solution. We'll do our distribution here to begin with. So we get 3 times 9, that should give me plus 27. 3 times 3m, that gives me plus 9m. Similarly, on the right-hand side, we have a distribution that leaves me with 14m minus 22, like this. So as I simplify here, now I can start to say, okay, well, 9m plus 5m, okay, that's another 14m plus 27. On the right-hand side, I get 14m minus 22. And you might say, okay, well, this looks like it's solvable. However, again, I want you to think about what would occur here if I replaced m with just any random number that I can think of, right? In particular, it's helpful, I think, to think about replacing m with 0. What happened to that value on each side? Well, on the left side, I get 14 times 0 is just 0, so I'm going to then add to 27. On the right-hand side, 14 times 0 is still 0, but I'm going to subtract 22. So if I think about this as a balancing act, the left side's always going to be 27 larger, the right side's always going to be minus 22, right? So there's this imbalance between each side. It looks as though I'll never make them equivalent to one another. And sure enough, as we show how by subtraction here, that we can move the variables to the same side, but they disappear, we'd be left with this false statement. Negative 22 is equal to positive 27. Since this is false, it implies that we have the contradiction, which tells me that the solution set is empty for this problem. The number of solutions is 0. Not that the value of m equals 0 is an answer, it's that there is no answer that makes for a true statement in the original problem. So these are the different types of classifications that you'll come across and need to be able to identify. This is also going to be true in cases where we look at inequalities in the next section. But just to recap here for a moment, the three types of equations we covered are the conditional, where we get one or more value for the solution. The identity is where all numbers are a solution, and the contradiction is where no solution exists. So be on the lookout for these different types of equations as we run through this section and through your homework. What I'd like for you to do is to consider taking a moment and see if you can answer these additional practice problems here at the end. All right, so thanks for sticking around. Hopefully we'll see you in the next video.